and I think on the green handout, the picture they give you, it's in the upwards position like this. And it's full of milk there. So when I'm swinging this milk pail like that, it's neither tension nor friction that's keeping the milk in that pail when it's in this upward position. So I'm not going to call it a major force and make a third case for it, because it's only going to show up in this one problem. So it is a possibility, but we're not going to encounter it a whole lot. So let's just talk about what takes the place of force centripetal in the milk pail problem. Again, that's the last one on the green handout. And it turns out that it's probably easier to look at it when it's down here. What is preventing that milk from busting through the bottom of the milk pail? Obviously, it is the bottom of the milk pail. And that bottom is causing the same force that we've met before, the same force that is causing me not to crash through this floor and this board not to crash through my oven top, and that is force normal. So that doesn't change when I swing this up here. It's still the bottom of the milk pail that is keeping the milk from spewing forth. Force centripetal, which is this way, is keeping the force centripetal is mv squared over r, and then there's another force that's countering that. Otherwise the milk would fall either this way or that way, and these are totally balanced. So let me make these vectors look about the same size. So force normal this way, and mv squared that way, force centripetal. So on number 5, use this formula. Force normal equals mv squared over r. I don't know if it was number 5, the last one on that sheet. So force normal is, in this case, mg. Notice the masses cancel on both sides, and g is going to be the acceleration due to gravity, 9.8. And from there, you'll be able to get the problem. You have to do that 3 different times with 3 different radii, but they're brief. All right, hopefully that helps on that. So just a reminder, lab is due when we come back, assuming that we come back. Well, if I see you on Monday, lab isn't due. The green sheet is due on Monday. Oh, we don't meet on Monday, it's President's Day. We don't meet on Tuesday, so because it's no physics on Tuesday. So I won't see this green sheet until Wednesday, and that is also when the lab is due. So hopefully you're using your snow time wisely. All right, now for the new material. We are going to find out that there's another force. We talked about tension and we talked about friction being causes of centripetal force, and just for a tiny whiny moment we talked about force normal, but we're going to drop that one. Let's just look at the third big player. So 1, 2, 3. There's another force out there, and it provides force centripetal, and it is in the case where, for example, the moon goes around the earth or the earth goes around the sun. That sort of scenario. So what is it that is holding the moon, what force, as it goes around the earth? The force of gravity. So that's going to be our third force. We have a formula for the force of gravity. So I'll call it F sub g for force of gravity, G m1 m2 over r squared. So we'll write that down and we'll identify the pieces of it. This stands for the force of gravity. G is a constant. You probably met it somewhere in your science past. And it is 6.67 times 10 to the minus 11. When you're putting that into your calculator, I recommend the button EE. It is a friend to you in this mod. It saves several keystrokes. So what you do is you put in 6.67 EE, And that is above, that's a second function above something. So look around your calculator and find it, EE. And then all you have to type in is -11. So when the calculator sees EE, it knows you're saying times 10 to the something, and then you tell it the something. So 6.67 EE minus 11 will tell the calculator this number. So we'll be using large numbers like that, even here and here and here. So it's nice to use that little shortcut. I think I've mentioned that to you earlier this year. All right, 6.67 times 10 to the minus 11 is the constant for gravity. And this stands for, when you have gravity, there's always two masses. So this is mass 1, mass 2. And this is the radius. As one goes around the other, it creates a circle. So the radius of the circle is represented there in the denominator, and it is squared. So that is our formula for gravity. So let me combine it and simplify this board with force centripetal. So whereas we did have mv squared over r equals t when it was tension, and it equaled mkmg when it was friction, now it's g m1 m2 over r squared. Let's, mathematicians, I need you on board now. I would like you to simplify this so we can use a simplified version and just speed up our work. I recommend doing it in the simplified version, but if you want to do it in this version, you will get the same answer as I will. So I'm going to multiply both sides by r squared. So that will create an r squared up here, and it'll disappear from here, and it'll create an r squared here. On this side, however, you'll notice the r in the denominator will simplify one of these r's in the numerator. So now that is become simplified. The r squared is now out of the denominator and is appearing like this. I can divide both sides by r and get it even more simplified. So I have r g m1 m2 equals mv squared. Now to complete the simplification, I have a mass here that I should cancel with the mass there, but which one? Is it mass 1 or mass 2? I'm going to shut down the video and start again so I don't go over my 15-minute limit. All right, be right back with you.